The civilization was desperate. They had built observatories spanning galaxies, peered into the quantum realm, and even colonized vast regions of the cosmos. But after untold millennia, they arrived at a startling conclusion. Their universe was not alone. It was merely one insignificant bubble in an infinite sea. This realization brought with it an existential crisis, not because they feared a cold, uncaring multiverse, but because infinity made measurement impossible. How common was their type of universe? What percentage of universes contained life? With infinity in the denominator, every calculation approached zero. Despite their incredible advancement, they knew absolutely nothing. Imagine for a moment that you're standing at the event horizon of a black hole. You know that once you cross this invisible boundary, there's no coming back. Everything that falls in is trapped forever, its information seemingly lost to the outside universe. But what if the very fabric of our reality, the universe itself, is actually contained within a black hole? It sounds like science fiction, but surprisingly, the mathematics of general relativity combined with quantum mechanics suggests this might be more than just an intriguing thought experiment. Let me take you on a journey that began with an insight from Einstein's field equations. When we examine the conditions that existed at the Big Bang, an infinitely dense, infinitely hot singularity, they bear a striking resemblance to what we believe exists at the center of black holes. This isn't a coincidence. The mathematics describing these two phenomena share remarkable similarities, and some physicists have suggested this is because our universe is actually the interior of a black hole that exists in a larger, parent universe. To understand this concept, we need to think about how black holes form in the first place. When a massive star dies, it can collapse under its own gravity, compressing all its mass into an incredibly small volume. At some point, the gravitational pull becomes so extreme that even light cannot escape, forming what we call the event horizon. But what happens inside? Einstein's equations actually break down at the singularity, unable to reconcile the extreme gravity with quantum effects. This breakdown might be telling us something profound about the nature of reality. Indeed, the 1960s, physicist Robert Dicke first proposed that our universe might be a black hole. The idea gained more traction in the early 2000s when physicists like Lee Smolin developed the theory of cosmological natural selection, suggesting that black holes might give birth to new universes. According to this theory, every black hole could contain an entirely new universe with its own physical laws, slightly varied from its parent universe. Evolution would then favor universes that produce the most black holes, explaining why our universe seems finely tuned for black hole creation. The mathematics supporting this idea comes from examining the total mass energy of our observable universe. If you were to calculate the Schwarzschild radius for all the mass in our observable universe, that's the radius at which an object of that mass would become a black hole, you get a value remarkably close to the actual observable radius of our universe. This could be a stunning coincidence, or it could be evidence that we're looking at our universe from the inside of a black hole. When we try to understand what happens at the event horizon of a black hole, strange things occur with time and space. From the perspective of someone falling into a black hole, nothing unusual happens as they cross the event horizon. But to an outside observer, time appears to slow down for the falling person, eventually freezing at the horizon. Similarly, our universe's expansion could be interpreted as us experiencing time within a black hole, while from the outside perspective, our entire universe exists in a frozen moment at the event horizon of a higher dimensional black hole. Think about this. The expansion of our universe accelerates as you move outward, approaching the speed of light at the observable boundary. This mirrors what happens near a black hole's event horizon, where space is stretched and light struggles to escape. The cosmic microwave background radiation, which we detect as coming from all directions, could be interpreted as the event horizon of our universe-sized black hole, eternally frozen from an outside perspective. The concept becomes even more fascinating when we consider white holes. These are the theoretical, time-reversed version of black holes. Instead of pulling everything in, they push everything out. Some physicists propose that the Big Bang itself was actually a white hole, the other end of a black hole in another universe. Matter that falls into a black hole could emerge from a white hole as the beginning of a new universe. The mathematics supporting this comes from solving Einstein's field equations in creative ways, producing solutions that describe such connections between black holes and new universes. One of the most mind-bending aspects of this theory involves dimensional shifting. In a four-dimensional space-time, a black hole appears as a three-dimensional sphere. But what if our parent universe has more dimensions than we do? A black hole in a higher dimensional universe could appear as a four-dimensional object to its inhabitants, which would manifest to us as our entire three-dimensional universe. This dimensional reduction could explain why we experience three spatial dimensions, when string theory suggests there should be many more. When scientists first calculated the entropy of black holes, they discovered something remarkable. The entropy wasn't proportional to the volume of the black hole, as you might expect, but to its surface area. This led to the holographic principle, suggesting that all the information contained in a volume of space can be represented on its boundary. If our universe is a black hole, then all the information in our universe might be encoded on its event horizon. In essence, our three-dimensional reality could be a projection of information stored on a two-dimensional surface. The mathematics of this holographic principle has been rigorously developed in string theory, particularly in the anti-de Sitter conformal field theory correspondence, ADS-CFT. While this correspondence was initially developed for a particular type of spacetime different from our own, the principles might apply more broadly. The equations show how gravity in a higher dimensional space can be completely described by a quantum field theory living on its boundary. If our universe follows similar principles, then what we perceive as reality could be encoded on the event horizon of our universe-sized black hole. Our civilization has only recently begun to grapple with the deep implications of these mathematical relationships. We've moved from the simple observation of patterns in nature, seasons changing, stars appearing in predictable cycles, to discovering complex mathematical formulas that govern physical processes regardless of location in space and time. We've mastered gravity and quantum mechanics, unlocking the secrets of what powers stars and how particles behave. But the question remains, how far can we push these ideas? The theory that our universe exists within a black hole isn't just a fascinating thought experiment. It could potentially address several puzzling aspects of cosmology. For instance, it might explain the arrow of time, which always moves forward in our experience. In a black hole universe, the direction of time would naturally flow from the singularity outward, aligning with our observation that entropy always increases. It could also explain the initial conditions of the Big Bang, which otherwise seem to require an extraordinary level of fine-tuning. The mathematics becomes particularly interesting when we consider quantum entanglement. When particles become entangled, they form a connection that transcends space. Changing one particle instantaneously affects its partner, no matter the distance between them. Some theorists propose that the space-time fabric itself emerges from these quantum entanglements. If our universe is a black hole, then the quantum entanglements forming our reality might connect to the parent universe through wormhole-like structures, as suggested by the ER EPR conjecture. Einstein-Rosen bridges equal Einstein-Podolsky-Rosen entangled particles. Consider the mathematics of the cosmic inflation that occurred in the earliest moments of our universe. This rapid expansion, which happened faster than the speed of light, has striking mathematical similarities to how space behaves just inside a black hole's event horizon. Near this boundary, space itself flows inward faster than light, making escape impossible. Inflation might have been the result of our universe detaching from its parent black hole, with the inflaton field representing the energy of this separation process. What about the total energy of our universe? When physicists calculate this value, taking into account both positive energy, matter, radiation, and negative energy, gravitational binding energy, the sum appears to be exactly zero. This zero-energy universe is precisely what you would expect if our universe formed from quantum fluctuations within another universe, like a black hole forming without violating conservation of energy in its parent universe. The equations balance perfectly, suggesting our entire cosmos might be an elaborate conservation of energy in action. The mathematical relationship between our universal constants presents another clue. The strengths of the four fundamental forces, gravity, electromagnetism, strong and weak nuclear forces, seem finely tuned. Adjust any of them slightly, and stars couldn't form, atoms wouldn't exist, and life would be impossible. If our universe evolved through cosmological natural selection, with black holes producing new universes with slightly varied constants, then the mathematical relationships we observe might be the result of an evolutionary process optimized for black hole production and, coincidentally, for life. Looking at the equations governing radiation from black holes, Stephen Hawking discovered that black holes aren't completely black. They emit radiation and eventually evaporate. If our universe is a black hole, could it also be evaporating? The mathematics suggests this might manifest as dark energy, the mysterious force accelerating our universe's expansion. As our universe black hole evaporates from the perspective of its parent universe, we might experience this as increasing dark energy, pushing everything apart at an accelerating rate. The rotation of black holes introduces additional mathematical complexity. Most black holes likely spin, creating what's called a Kerr black hole. These have two event horizons and a region between them called the ergosphere, where space itself is dragged around the black hole. If our universe formed from a rotating black hole, the mathematics predicts we might see evidence in the large-scale structure of our cosmos, perhaps in a slight preferential direction in the cosmic microwave background radiation, something that some studies have actually hinted at. Perhaps the most profound implication of the black hole universe theory relates to what physicists call the measure problem in cosmology. If the multiverse contains infinite universes with infinite variations, how do we calculate the probability of our universe having the properties it does? This problem dissolves if universes form through black holes, as each universe would have finite volume and energy, creating a natural measure for probabilities. The mathematics becomes calculable again, allowing us to potentially predict features of our universe from first principles. What does all this mean for our civilization's quest for knowledge? If the mathematics is correct, and we truly exist within a black hole, we might eventually reach the limits of what we can discover about the larger multiverse. Just as someone inside a black hole cannot access information from outside the event horizon, our observations might be fundamentally limited by our cosmic boundary. However, the mathematics also suggests potential loopholes. Quantum entanglement, wormholes, or Hawking radiation might provide subtle ways to infer properties of the parent universe. Our journey from simple pattern recognition to complex mathematical models of reality has led us to the brink of an even greater revolution in understanding. The boundary between philosophy and physics blurs when we contemplate our universe as a black hole. The mathematics doesn't just describe this possibility, it nearly demands it. The equations of general relativity, when pushed to their limits and combined with quantum field theory, point toward a cosmos where black holes aren't just objects within universes, but the birthplaces of universes themselves. The implications extend beyond just physical reality. If our universe is one of many born from black holes, then our understanding of fundamental physics might be shaped by a form of cosmic evolution. Our physical laws wouldn't be unique or inevitable, but rather one set among many possibilities, a set that happens to be effective at producing more black holes and, consequently, more universes like ours. The mathematics of natural selection would apply not just to biological systems, but to universes themselves. As we stand at the edge of this profound realization, we must acknowledge both the power and limitations of our knowledge. The mathematics tells us that our universe might be a black hole, but proving this conclusively might remain beyond our reach. Yet even if we cannot directly observe the parent universe, understanding our place in this larger cosmic structure could revolutionize physics, providing a framework to unite quantum mechanics and general relativity into a cohesive theory of everything. The great irony is that while black holes were once thought to be the ultimate destroyers of information, they might actually be the ultimate creators, the wombs of new universes. The mathematics doesn't just allow for this possibility. It weaves an elegant narrative where our cosmic beginning, the Big Bang, was actually a cosmic transformation. Matter from one universe passing through a black hole to seed an entirely new reality with its own space, time, and physical laws. So, the next time you look up at the night sky and ponder the vastness of our universe, consider this. You might be looking out from within a black hole, your gaze never truly reaching beyond the cosmic horizon that defines the boundary of our universe. Sized black hole. The darkness between the stars isn't just empty space. It might be the shadow of a greater reality that mathematics alone has allowed us to glimpse. The mathematics says, yes, our universe could indeed be inside a black hole, and that realization might be the key to unlocking the deepest mysteries of existence. As the ancient civilization in our opening story discovered, even with all their technological prowess and scientific advancement, the cosmos still holds mysteries beyond our immediate grasp. Yet unlike them, we need not despair at the vastness of what we don't know. Instead, we can marvel at how mathematics has allowed us to peer beyond the veil of our observable universe and contemplate our place in a potentially infinite cosmic tapestry. Perhaps someday, we too will master energies beyond our planet, our star, and even our galaxy, continuing our quest to understand not just our universe, but the greater reality beyond our cosmic horizon.